I'll begin. Dear Heavenly Father, we thank you for this day. Thank you for these students. Just ask you to bless our time together, Lord. In your name I pray. Amen. Okay, so I will now foolishly attempt some sort of motivation for why the following formula is true. So this is the polar change of variables theorem for polar coordinates, right? What's it look like for polar coordinates? The statement is something like this. If we take the integral, I'm going to start with the polar side, actually. So if we take a region, let's say S, which is written in terms of polar coordinates, and we integrate f of, our cosine theta, our sine theta, and then times r dr d theta, allegedly that will be equal to the integral over the original region of f of x comma y dx dy. So this is the change of variables theorem for polar coordinates. So, Emily, I will come back to the general change of variables thing and we'll answer your question there, hopefully about 10 minutes. All right, so what I want to try to do is just to look at a specific picture and try to sort through why this should be true. Maybe we can do that. So, let's see here. So let's let the polar region be relatively nice, and I'm going to draw the picture in the Cartesian plane, but it's something like so. Suppose the region actually looks something like this. This is actually my R. All right. So in other words, R, if we are to describe it in polar coordinates, it's, R is xy. What is it? It's the x comma y such that what? Such that, theta 1 is less than or equal to theta 2, less than or equal to theta is less than or equal to theta 2, where I'm talking about the polar coordinate theta of that point xy. All right, and on the other hand, the R. So maybe this is R1, this is R2. We also have that the radius is between R and R1 and R2. Okay. So if I take this shape, right, and I divide it into like a grid, but a sort of polar grid, right? Something like that. Then I can ask, what's the, of course, the three-dimensional picture, I should think about skyscrapers over these to think about the volume that's, So this, again, this is actually the picture of R. Of course, the one thing we could do is just calculate it like this, as we've done, right? We could use xy coordinates to calculate it directly. That would be a real pain for this shape, wouldn't it? Because this is neither type 1 nor type 2. It's some sort of, it would be really unpleasant. I guess you have to break it into two pieces to do two type 1s or two type 2s if we were going to calculate directly in terms of Cartesians, right? But what I'm proposing is that we can also think about setting up the volume over this, half-eaten slice of pizza. Somebody with really, really symmetrical teeth, I suppose, or just an obsessive, compulsive need to eat their pizza in a very, very neat and nice way. But I guess we could add in variable radius to make it more realistic. But anyway, the point is that we could just set, okay, yes, we can divide this up into pieces and do that. We've already done that. But we could also take this and set it up in terms of polar coordinates, all right? And so each one of these, like, let's look at this particular point here, I could say is that would be at the maybe, how to say this? That's at the ith radius, and it's at the jth value for theta, that point right there, right? And let's just, for the sake of simplicity, I'll use the lower, sort of these corner points to define the height over these things. So f of this would be the height of the ijth skyscraper. But these skyscrapers are these are a little bit more sophisticated than the ones we talked about before. Because if I was so foolish as to try to draw this again over here, we're talking about this sort of shape like this, right? Here's my foolish attempt at the grid again in the xy plane, visualizing this as my r, right? Then the so far unpictured, but now I'm about to picture it, function f, right? We would be thinking about, solids over these non-rectangular little sector things. And so if this is, I don't know, if this is the ijth one, then, there's some kind of, it's got one side that's curved, right? I mean, it's a very elegant modern skyscraper. It's got two flat sides and two curved sides. This would be a real pain to build. We got money to build it here, though. I'll tell you that right now. Sorry, it's unnecessary and kind of stupid. But the point is the volume of this, right? It would be the area of this thing, right? The area of this thing times the what? Times the height, right? That would be the volume of that one skyscraper. And you can think about putting one at each one of these little grids, right? That would be another way to calculate the volume that we're describing with that Cartesian integral, right? Are you guys with me? Okay, but so we figured the height would just be the usual thing. You just evaluate the function at that point. That gives me the height, right? But by the way, this is I really should put some quotes here, because we don't feed r and theta directly into f, right? To use f, I have to give the x and y values, right? So I take this r sub j and theta sub j, and actually what I should put here is f of r sub j cosine theta j, r sub j sine theta j, to be more not both j's, r sub I, right? R sub I theta sub j. So that would be the height of this one, and then to get the total volume, what do? Well, I still need to figure out the area. What's the area of the sector? So let me draw it again over here. So the sector we're talking about, right? I'm saying that this is where we have r sub I and theta sub j, right? So let's suppose that this over here is still r sub I and theta sub j plus 1. This right here would be ri plus 1 theta j. And my enumeration up here would be r sub I plus 1 and theta j plus 1, right? But what we're going to do is just say, okay, well, that's really r sub I plus the delta r and theta sub j plus the delta theta. In other words, we're going to assume that this grid is regular, that it's got the same change in radius going from one band out to the next, and you got the same change in theta going from one band out to the next, right? So what I'm trying to say is that this is delta r, all right? And if I could extend this back, this would be delta theta, all right? So if that's delta r and that's delta theta, what is what's the area of that sector? It's what? It's 1/2 r sub I, right? delta theta squared. Oh, I'm sorry, delta theta squared? No. What's the formula for area of a sector? Let's see here. So we start out with 1/2 r sub I plus, so r plus delta, r sub I plus delta 1 squared delta theta. Then that minus 1/2 r sub I squared delta theta. See what that does? That takes the area of the whole pizza pie, right? And it subtracts off this piece right here, which we've eaten to calculate the area of just this piece here. And so what is that? Well, that's 1/2, right? R sub I squared plus 2 r sub I delta r plus delta r squared minus r sub I squared times delta theta. So what happens is these cancel, and you're just left with r sub I delta r delta theta plus 1/2 delta r squared delta theta. So the volume would be basically the limit as n goes to infinity. Let's say m goes to infinity. The limit as n goes to infinity of the sum I equals 1 to m, the sum j equals 1 to n. We've got f of r sub I cosine theta j, r sub I sine theta j. And then I need my formula for the area of the ijth sector, which we just worked out is apparently r sub I, right? R sub I delta theta delta r, right? Plus this pesky 1/2 r sub I cubed, or r sub I times what? I forgot. I can't read my own. Delta r times delta r squared delta theta, right? Yeah.
Were you leaving out a pi on all this?
Thetas and radians, it's got the pi built in. Yeah, so the formula for a sector of a circle, 1/2, but good question, r squared delta theta. So what happens with that formula when theta, delta theta is all the way around 2 pi, the 2 pi and the half cancels to give us pi r squared, which is, of course, the area of a circle. And all this relation really says is that the area of a sector is proportional to the number of radians subtended. Anyway, so here, over there, yep.
So on the second part of the end of the equation, you have r sub I, but then down there you don't have r sub I.
It's because I just made it up. Thank you. Yeah.
Are you planning on doing attendance?
Ah. No. I forgot to bring it. So actually, if someone would rip out a sheet of paper and start a list of names, it would be awesome. Thank you. Your name? Joshua. Joshua. And Mr. Other Joshua. You're Joshua as well, right? Conspiracy of Joshuas. Josh started it? Hey! Whoa. Cool. Are there any other Joshuas in here, or am I safe?
You called him Joshua once.
I did? Oh, yeah, sorry about that. Don't mean to insult you as someone who's obsessed with attendance. Let's see here. Although I'm just learning that now. No. Okay, so anyway, the point here, guys, is this is just a way of rewriting that specific kind of volume, signed volume. We can recast it in terms of polar coordinates like this. And I'm saying that if we take the limit as that grid gets smaller and smaller and smaller, then this should actually reproduce the sign volume that we already have all of our Cartesian techniques to calculate, right? And you see where the r is coming from. It's coming from the way the area of the little grid is related, right? The little delta r, delta theta. What is the area associated with that? Well, it's r times delta r, delta theta. What's the area associated with a little Cartesian delta x, delta y? Well, it's just delta x, delta y, right? So now what happens here? In the limit, and so the rest of it to be, I mean, I can't really be careful. We're not that careful in here. But for reasons I can't get into, since this is third order small, this integration, that vanishes in the limit actually. So this piece it goes away because it's third order small. This, on the other hand, is only second order small, so it survives. That's why this is way, way bigger than that in the limit of these deltas going to 0, which is implicit within m and n going to infinity. How are delta r and delta theta related? Right, delta theta is what? It's theta 2 minus theta 1 divided by what? Delta r is what? r2 minus r1 divided by what? In my setup, n over m, I guess, and n, right? I goes with the r, j goes with the theta, is that right? Yeah. Yeah. So as m and n go to infinity, these deltas get super tiny, and so that third order small one just goes away. What are you left with? This is nothing more than the Riemann sum, right? This is the integral, theta 1 to theta 2. Well, let me just write it this way. It's the integral, double integral, over the rectangle, r1, r2, Cartesian product with theta 1, theta 2. This is a rectangle in the r theta plane, right? Like that. And, well, and that's f of r cosine theta, r sine theta, and then r d theta dr, which is the theorem. I would say that this has been a successful discussion, but that depends on what time it is right now. 20 minutes, okay. Any longer than that, I would have deemed it unsuccessful. Because, of course, this really doesn't help you do problems, right? But I hope it does help demystify this formula a little bit. It's really just coming from rewriting the integral in terms of the other coordinate system. Okay? Now, more generically speaking, I wouldn't try to draw the picture for the generic one, but the theorem, right, is what? The integral over the transformed region, let's say t of r. Well, let me go backwards here, the other way around. So let's say the double integral over r of f dA is equal to the double integral over t of r of, well, really f composed with t. And then we actually have the determinant of t prime. No, fine. I can't be that. Words. F of x of u comma v comma y of u comma v. And then the absolute value of the partial x comma y with respect to u comma v. Du dv. So here, this t, I'm thinking of t of, let's see here. Well, this is the transformed region anyway. I'll just stop at that. So you're asking me a question about the homework. So this quantity on its own, I will refer to as dA in the new coordinate system. I mean, that is what dA is. That's the infinitesimal area element in the uv coordinates. So we have to multiply by the absolute value of the Jacobian. So in the polar coordinate case, this dA just worked out to the rd theta. Now, the one you asked me about was three-dimensional. So in the three-dimensional case, we have some region, let's say w, like we did. So you got f dv, right? And so you look at the transformed region of w, and you look at f of, well, fine, x of uvw, y of uvw, z of uvw, so much writing. Absolute value of the Jacobian of x, y, z, partial uvw. Sorry, this is about the third time I've written this in here, but I think it's worth our time to write it. Every time you write it, you get closer to understanding it. It's true. And this quantity on its lonesome, I refer to as the infinitesimal volume element. This is dv. Of course, in the Cartesian world, so we have, it's probably useful for me to make a catalog of some of these that we've already learned. All right, let me collect our thoughts a little bit here. So, typical coordinate system. All right. And I'll say, all right, so if we have Cartesian, and we're talking about R2, then we've got dA, and we just think about that being dx dy. Right? If we're talking about polar coordinates for R2, then that gives us dA is r d theta. And in terms of standard coordinate systems, that's pretty much it. I mean, there's no other coordinate system that I use on the plane in a standardized way except for polar coordinates. All right? But if you were to do, say, uv coordinates on R2, all right? If you were to consider some coordinate system, say the uv coordinate system, then your dA would be the Jacobian of xy with respect to uv, absolute value of that, du dv. Let me give a specific example of this. For example, we could be looking at, how about this coordinate system? The coordinate system that's built, this is a weird coordinate system, right? But check this one out. Maybe we have, I don't know, if you look at ellipses, you could look at ellipses in the plane, right? Of the form what? Maybe, what is this? Which one's got bigger, x squared or y squared? The x squared is bigger. So maybe this is 2x squared plus y squared equals to constant, right? And then, let's see here. The other thing I could do would be to look at lines of slope, lines from the origin. So, like this, this has slope m. So this is kind of out there, but let me suggest that we could let u equal to 2x squared plus y squared, and we could let v equal to the slope m. Now, how could I get the slope m in terms of x and y? What makes a good coordinate system, by the way? If we're talking about the plane, the coordinate system, whatever it is, it has to be some pair of numbers which uniquely fixes the point, at least for some big region of the plane, right? X, y coordinate. If you tell me how far over in the x and how far up in the y, that uniquely fixes a point in the plane, right? r and theta, that works out just much the same, right? If I tell you how far it is from the origin and I tell you what standard angle, that uniquely fixes a point in the plane, up to the degeneracies of polar coordinates, which we are fond of ignoring, right? That all breaks down at the origin, and we do get into trouble with degeneracy of angles. Setting those nuances aside, polar coordinates are mostly good. So my claim is that if you tell me a slope, right, and you tell me the value k for a particular ellipse, that uniquely fixes a point. Like, if this is the k equals, if the first one inside is the k equals 1 ellipse, and I tell you that you're at slope, m equals to 1, that uniquely fixes like that point. There's no other point in the plane that comes from a line from the origin with slope 1 that falls on the ellipse that works out to x squared plus 2x squared plus y squared equals to 1. Yep.
Wouldn't the line with slope 1 also go into the third
Curses. You got me. So you have a very good point, which is that lines go through the origin. They don't start at the origin. And so I'm going to have a problem. You're right. So let us assume that x is greater than 0. There we go. So, fixed. But no, thank you. I very much appreciate that. That's a fantastic comment. Really is. Now, but my point here is slope m, this is y equals mx, right? So if I want to get a formula for m in terms of y and x, I just do what? Yeah, y over x. Now, at this point, you'll be frustrated because to calculate this, we need to calculate what? This is, what does this mean? This means the determinant of x u x v x, I'm sorry, x u y u x v y v, right? But you see, that's a pain because we don't have x and y as functions of u and v here yet, do we? There's a wonderful theorem, though. And this theorem I will share with you because it will get you out of a pickle like this. And the theorem is this. The partial uv, partial xy, right, is actually equal to 1 over this. This is actually true. Where I mean, if you'll allow me this small manga-style calculation, this is the determinant of u with respect to x, v with respect to x, u with respect to y, v with respect to y. And so I can calculate the reciprocal Jacobian here pretty easily. Because I already, you can see what the partial derivatives of u and v are for x and y here, right? Right, so I'm getting there. So so continuing my discussion here, dA would actually be equal to du dv divided by partial xy, partial uv is what I'm claiming. That's actually a theorem. And so that's du dv divided by the determinant of what? So what's ux? We got 4x. What's vx? So partial differentiate v, we get minus y over x squared. Yeah. What's xv? Excuse me. What is u sub y? Yeah, 2y. And what is y sub v? I'm sorry, I can't say words. What is v sub y? I'm trying to do this calculation right here. V sub y. What do you say? I heard somebody say 1 over x. That's very good. So here we go. This is du dv over what? 4 minus, what is that? 2 y squared over x squared? Yep.
Why can you go from multiplying the du dv by the Jacobian to dividing it?
Ah,
It wrote it backwards.
I'll explain in a minute. What's that?
Wouldn't it be partial uv over partial xy there?
Yes, and that's what that is what I calculated, but you're right.
That was my question.
That is a good question. And the larger question is, why is this allowed, right? And I actually I can explain that. But let me put that off for a little bit. Okay, sorry, that was a typo. Yeah.
Also,
Uh-oh.
isn't it plus? I mean, I don't know determinants, but isn't it?
No, you apparently do. That is plus, because minus a minus gives me a plus.
Yeah.
So, yeah. Now here's a larger criticism is we'd like a formula just in terms of the UV coordinates, right? So this y and x are out of place. They're out of order. Can you tell me how to rewrite this in terms of how about this? Yeah, that's just v squared, right? So this is actually du dv over 4 plus 2v squared. So there you go. There is a very non-standard area element in terms of this slope / which ellipse do you sit on coordinate system in the plane. Not a coordinate system I recommend, but I assure you there's some problem which it really helps you solve. So the reason this makes sense actually is just a little bit of linear algebra. Essentially, we have t of something like t of xy is equal to u of x comma y, v of x comma y. And we have the inverse transformation is x of uv, y of uv, like that. But the larger point is that when you take t and you compose it with t inverse, what happens when you transform the coordinates and then you transform them back again? Well, you just get back where you started. You get back where you started again. So the larger point is that t composed with t inverse is actually the identity map. And if you take advanced calculus, one of the things you learn is that we can calculate the differential of this. So the Jacobian of t times the Jacobian of t inverse is equal to the identity matrix. And then there's this, in linear algebra, you find out that the determinant of the product is the product of the determinants. But this this thing right here, JT, is exactly the partial u v x y. And this is our notation. Our notation for that is this. Don't worry, I won't charge you for teaching advanced calculus. I know you didn't pay for that. Nor will I test on this because, as you can tell, I am well outside the boundaries of this course proper. But really, the explanation for why this is true comes from linear algebra and the study of advanced calculus. The fact that we can talk about the coordinate transformation and its inverse transformation, and the Jacobians have to be inverse for these reasons. So, but this is a nice trick when you don't have like nice formulas for x and y in terms of u and v. There exist homework problems like this. I have found them before and not known about this, and then went to the trouble of solving for x and y in terms of u and v. And sometimes it's really quite unpleasant. So this is a nice runaround for that. All right, I am way in the weeds right now. Let me get back to the hunt here. So 3 dimensions. How about 3D? In 3 dimensions, we have Cartesian R3, right? And so there we start talking about the volume element. And so the first thing, dx, dy, dz. That's the infinitesimal volume element, right? If we use cylindricals, cylindrical coordinates, then we use dv is r, dr, d theta, dz. All right? Let me work that out. What is the cylindrical coordinate transformations? We have x equals to r cosine theta, y is r sine theta, and z is, well, z. Okay? So partial x, y, z with respect to r theta z polar coordinates, right? That's the determinant of, we got, I'll write it out symbolically here for a second, x sub r, y sub r, z sub r, x sub theta, y sub theta, z sub theta, x sub z, y sub z, z sub z, z. Okay, so that is actually the determinant. So we got, this should be very reminiscent of like the last thing, last class, remember? We did the polar, I think, if I remember right. It's almost the same stupid calculation. It's just now it's inside a 3x3 matrix with some zeros. So that works out to r cosine squared theta plus r sine squared theta, all right, times 1, also known as r. So that's cylindrical coordinates, r d r d theta dz. And then spherical coordinates. Spherical coordinates, we suffered through this yesterday, remember? Never to be done again. Well, never for me to do again. Maybe you'll do it in the next test. Let's see here, sine phi. Am I evil? No. I tease because I love. Let's see here. So that is the spherical volume element, rho squared sine phi d rho d phi d theta, right? Generically speaking, so, for, others, you have something like x is equal to x of u v w, right? You have y is equal to y of u v w, right? Suppose you have some other coordinate transformation. Z is actually can be written as a function of u, v, and w. In other words, you got this u, v, w coordinate system, right? And there, the infinitesimal volume element is the absolute value of the Jacobian times du, dv, dw. So getting back to your question, finally, Emily, you asked me about that homework question. It's like way at the end. What is my exact wording? Find the Cartesian volume element for say again, it's du what? Uh-huh. 2 dx dy dz, right? Where cosh phi, and y is equal to, okay, and z? Oh, you just did, so, yeah, sinh. So in this problem, u is like u. The v we could take to be theta, right? We could think about v being theta, and think about the w being the phi, right? And that would, and this would be the relation, whatever that works out to. By the way, do you guys have any sense of what on earth this weird coordinate system is? Hyperbolic, yeah, something. Let's see here. What if we look at x? What happens with x squared plus y squared? With this coordinate system, we get, you see, we get u squared cosine squared, u squared sine squared theta. So the thetas squish and just give us a u squared what? U squared cosh squared phi, right? And then z squared is what? U squared sinh squared phi. So this coordinate system is based on thinking about x squared plus y squared minus z squared being equal to u squared. So the u is, in some sense, telling you which hyperboloid of, I forget, 1 or 2 sheets that you're on. So that's the meaning of u. It's kind of taking the space and chopping it up into hyperboloids, and your choice of u will put you on a particular hyperboloid. And then once you're on that hyperboloid, theta will pick you, kind of spin you around and pick you a certain direction on that particular surface in the space. And then the phi, what's that do? Well, it's something like this. The u picks out, like a particular hyperboloid, part of the hyperboloid. Or maybe, I don't know, guys, if it's a hyperboloid. Can you guys help me out, put me out of my suffering? If we have plus, plus, minus, is that 1 or 2 sheets? 1 sheet? That's what you remember? So if there's two pluses and a minus, it's 1 sheet? Okay, yeah. So it's one of these deals, right? Ah, sad. Right? And of course it goes on and on, but there's just 1 sheet. So you give me a value for u, it picks out one of these hyperboloids of 1 sheet, and then inside that 1 sheet, you can use the theta and the phi to pick a particular point in there. So theta and phi serve as sort of coordinates on the hyperboloids. I mean, it's a really kind of a really weird way of taking 3 dimensions and chopping it up into pieces, but that's what the geometry behind that. Do you need to do any of this to solve that problem? Nada, right? I mean, that problem is completely, I think, solved by this formula right here alone, because this dv, remember, is dx dy dz. That's always our starting point. dv is dx dy dz. dA is dx dy. Yep.
What's the formula to do the Jacobian for S3?
I will tell you. So here's the determinant of a 3 by 3 matrix. A, B, C, D, E, F, G, H, I. And while there are, of course, dozens and dozens and dozens of tricks, this formula will work. So A times E, I minus HF minus B times DI minus GF plus C times DH minus EG. Let me color code the meaning of that for you. So what I'm doing is called the Laplace's expansion by minors across the top row. So first of all, this A is that A. And then whatever's not in the first row and first column gets put over in here. So remember the determinant of the 2 by 2? Right, AD minus BC, like that. So this is actually the determinant of the 2 by 2 that's not in that first row and first column. Then B. Well, the thing is, there's a plus, minus, plus, minus, plus, minus, plus, minus, plus pattern for Laplace's expansion by minors. You're like, could you explain that? If we had a week, sure. But we don't. So, and it's beside the point. We just need this formula here for our purposes. So you cross out the second column and first row. What's left is these guys. So this right here is the determinant of DFGI, right? And then finally the other, I'm trying to explain the formula to you, Emily, so you can remember it forever and ever. Because if you're taking this class, You need to know this formula for future classes, right? You're going to take 221. Am I right? You're currently taking 221. Am I right?
Yep.
Yeah. So it's still relevant. You're still in the class. It's not over yet, right? So then the C, this right here is the determinant of everything that's not in the first row and third column, namely the determinant of D, E, G, H. Now, if you're in Math 221, you either have learned or you will soon learn a whole smorgasbord of shortcuts for particular special kinds of, like, if it's diagonal or it's triangular, blah, 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 blah. You can expand on any column, any row. There's all kinds of other things you can do. There's the cross, cross, cross rule, which only works for 3 things. Some of you tried to do it for 4 on the test. Lost your points. You know what I'm talking about. I talked to Dr. Smith. I'm very disappointed. I was planning on working a very particular integral for you guys today. What I wanted to do was to look at the shape something like this. We have a plane. We have another plane. And then we take a cylinder like that. And then we look at the shape that's between this and that and here and do an integral over something like that, like a unevenly sliced cylinder. This makes a really good a cylindrical coordinate change example, or perhaps polar coordinates, depending on how you start. But we'll do it tomorrow. So, thanks, guys.
You told us what usually happens when you plan.
Yeah. Well, I can make those kinds of plans are okay. But yeah, actually, a fair point.